Ask him. Answer. Okay, okay.
Dear participants, a very good morning. Am I audible?
Yes.
Yes.
Thank you for joining with us for the first session of 3 days FDP. This is our fifth session and first session of third day. Our eminent speaker have already arrived. He is with us. I will give for him a short introduction. Our fifth session will be conducted by Dr. Shantanu Giri. We are very pleased to have him with us. We are very glad. Thank you, sir. Dr. Shantanu Giri is currently associated with Haldia Institute of Technology as an associate professor. Previously, uh, he was working as assistant professor in Haldia Institute of Technology in the Department of School of Applied Science and Humanities. He has lot of academic experience, including more than 7 years in teaching and post PhD research of more than 3 years. He is also acted in NIT Rourkela as a DST inspired faculty. He also served Virginia Commonwealth University as a postdoctoral research fellow. He has several awards and recognitions, including DST Inspire Faculty Award 2014 and Lilly and Company Asia Outstanding Thesis Award in the year 2011. He also an awardee of Shanti Ranjan Palit Memorial Award in the year 2009. He is a reviewer of several journals, including Molecular Modeling, Journal of Physics and Chemistry of Solids, International Journal of Quantum Chemistry, Chemical Physics Letters, Physicia E, RSC Advances, and many more. He has also guided one PhD scholar, and he has ongoing 3 PhD scholar. He also supervised MSc thesis, many numbers. His total publication is around 140 with citation of nearly 2,800. He has several journals and book chapters. He has ongoing sponsored project number 4. He has completed 2 DST inspired and SERB sponsored project, and there is ongoing 1 DST SERB projects going on under him. We are very glad to have him with us. He will deliver his knowledge and some academic information regarding renewable energy resource. So, sir, over to you.
Yeah, am I audible?
Yes, sir, you are clearly audible.
Okay, so first of all, I would like to thank Subhankar for inviting me to give a lecture in this faculty development program on renewable energy resources. Let me start by sharing my slides. In that slides, I will share some of my work along with the recent developments that we are currently working in our lab at Haldia Institute of Technology. So, is it necessary to switch on my video? Because
No,
of
no,
the
sir,
later.
it's not necessary.
Okay.
Without video, you can continue.
Is this slides are visible?
Yes, sir. It's clearly visible.
Okay, so today I will give a little bit brief introduction about the development of new generation hydrogen storage material and a little bit of lithium-ion battery electrolytes and the additives, and a little bit about the small molecule activation to gain some energy. So as already in the introductions are already discussed, currently I am working in Holder Institute of Technology in the Department of Applied Science and Humanities. So mostly I will share the works, whatever I have done in this institute. So why we need this renewable energy? Basically, means the human, we are mostly using the fossil fuel at different sources. So gradually it is decreasing. So there is a need to have some alternative energy resources that can fulfill our demands. So in this aspect, hydrogen is considered to be a safe and renewable alternative fuel due to its several reasons. The reasons are basically it's a very abundant element and it does not produce harmful emission. If it is burnt, it can always produce the water. And it has a very nice fuel efficiency. So coming to the hydrogen storage, there are two different ways we can actually store the hydrogen. One is the physical mode, in which we can compress that, but also it requires a high pressure. And we can compress its a cryogenic temperature also, or we can use the liquid hydrogen. Among the material based, basically there are several ways to store the hydrogen. People are mostly working on that nowadays to develop a certain material which can efficiently store hydrogen. The advantages of this storage is that we can get the high volumetric and gravimetric density. And we have to keep in mind that once the hydrogen is stored in that material, it should eject whenever it's required. So there should be a thermodynamic reversibility. And mostly the hydrogen can be stored in the material in very low temperature and high pressure. So there is a need to store the hydrogen in the ambient condition so that we can use the hydrogen. So there are so many different ways we can actually store the hydrogen in materials. Like we can use the metal organic framework that I have. This is the mentioned metal organic framework. Organic liquid, this type of organic liquid can actually store the hydrogen. We can have the hydrides material. We can have the complex hydride, like here sodium aluminum hydride. We can have calcium borohydride also. And we can have the chemical hydrogen like this NH3BH3 complex. We can have a lot of hydrogens here in this particular complex. And from the basic chemistry point of view, we can understand this complex is nothing but a Lewis acid-base complex. So I will talk about mainly some organic framework in this lecture, which can store hydrogen. So these are the preliminary things that we can store hydrogen efficiently, either in a physical mode or in a chemical mode. But before going to start in detail, let me tell you that absorption of hydrogen that should be in the fission mode, because if the hydrogens are stored in the chemisorption mode, that this hydrogen is very difficult to reuse. So we need to develop some kind of material or some other organic substance that can store hydrogen in a physical way, or rather we can say in the molecular form, so that the hydrogens can be used whenever it's necessary. So when I am talking about the fission, that means the binding energy of the material along with the molecular hydrogen should be not that much high, so we can break that hydrogen bond. Okay, so these are some cartoon diagram where I have shown that so many countries in our in recent time, they are actually focusing on the renewable energy resources rather than using the traditional fossil fuels. So mostly I have shown here the solar and the wind power, and Denmark is actually using their more than 50% from the wind power and very few the solar power. And till now, India is lack of that particular race, and still we are using that traditional energy resources. But there are several projects are going on from the hydrogen storage as well as some alternative energy resources. The research are going on, and hope in the coming days we also will come into that picture where we can use more renewable energy resources rather than using the traditional energy resources. So first, let me talk about what I have done some work on the organic framework. Here you can see this is a benzene molecule, we all know, and we can absorb the lithium on this benzene molecule and it can form a star-like compound. So this lithium, when it absorbs on benzene, it carries a positive charge over this lithium, like this. This is the positive charge carries over lithium. So what will happen? The hydrogen, when it comes to that lithium, it can bind in Fischer fashion. You can see here there is no such bond between two hydrogen molecule, rather they are still in the molecular form, but there is no bond. That means whenever it is necessary, we can use that hydrogen, and up to 9.6 weight percentage, we can gather the hydrogen in that particular molecule. So we have done this work in back 2013, and now the material has been modeled and the experiments is going on so that we can have some kind of material so that they can store the hydrogen. So if only one benzene with 6 lithium can trap 6 hydrogen molecule, then we can imagine if we can produce the material, it can absorb a lot of hydrogens. And since this is the physics option of the hydrogen molecule of this benzene, we can use as a potential hydrogen storage material. Okay, so here are the different organic molecules. Those are organic chemists here in this platform. They can understand these are a very simple organic molecules starting from the pyridazine to pyrazine, and these complex actually observe the lithium, not only lithium, sodium, potassium, and that sodium, potassium, lithium can absorb so many hydrogen molecules. So these are the ground state geometry of this hydrogen trapped organic system. We can see that the one lithium can trap 3 hydrogen, whereas one potassium can have 8 hydrogen molecules at a time. But in the gravimetric weight percentage point of view, I would prefer the lithium because it's a lightweight rather than sodium and potassium. So even if potassium can trap more hydrogen than lithium and sodium, still lithium-based complex will be preferable for the hydrogen storage. Okay. So here I have shown this binding energy of these 3 compounds that we have taken with the lithium, sodium, and potassium. As you can see that the binding energy in the pyridazine complex is less than the other 2. That means in that particular complex, the removal of hydrogen will be more easy than the other complexes. So like that, this we are in a process to develop the material out of this building block so that we can have some kind of material. Okay. So once we have the hydrogenated system, it is our duty to see whether that particular complex is really stable or not. If it is unstable, then there is no point of use those molecules for the further material synthesis. So here, this is a potential energy diagram of that lithiated complex. The red one is for the lithium with 5 hydrogen, and the temperature is 50 K. As I mentioned earlier, that we need very less temperature or very low temperature to absorb molecule, and as you can see, there is no such fluctuation in that particular complex when we do the 1000 femtosecond trajectory. So that means at 50 K Kelvin temperature, the lithium can efficiently bind 5 hydrogen, and as we increase the temperature at the room temperature, then there will be more fluctuation. That means that the hydrogen will be gradually detached from the parent moiety. So the mechanism is like that. You keep the temperature very low while you store the system, and then when you need the hydrogen, you just increase the temperature, then the hydrogen will be liberated. And again, you decrease the temperature, that particular molecule can absorb the hydrogen. So here we have shown the pyrazine lithium complex and pyrazine 2 lithium complex, and we can see that up to that in the normal room temperature, they can actually liberate the hydrogen molecule. So the reversibility criteria, which is one of the major criteria of the hydrogen storage, that can be fulfilled in those systems. You can see here I have given some snapshots, like when we are performing the 1000 femtosecond trajectory and the 100 femtosecond at 50 K, you can see all 5 hydrogens are actually surrounded by lithium. But once we keep on moving the trajectory, one by one, the hydrogen molecule is ejected. So here start from the 5, now we can have only 3 molecules. So that means two hydrogens already liberated. So whenever I need, we can tune the hydrogen storage and hydrogen use by tuning the temperature only. So here also you can see the 2 lithium can uptake up to 10 hydrogens at 100 femtosecond, which is very small time scale. We can see some of the hydrogens are going out from the lithium, and here in the 500 femtosecond, in this particular lithium, there is no such hydrogen. So that means if you just simply increase the temperature and over a time span, we can have the liberated hydrogen. So work is going on this particular system to model the material. These are the building blocks, and if the building blocks can uptake is a high percent gravimetric weight percentage storage, then we can really use this type of complex in the material for the hydrogen storage. So this is another organic molecule which is triazine based. That only difference from the previous work is to the difference in the number of nitrogen molecule, because the nitrogen molecule is bind with the lithium. So we thought if I increase the number of nitrogen molecule, then we can trap more lithium in a system. As a result, more hydrogens can be trapped. So as you can see here, this system can take up to 3 lithium at a time. So this is the triazine system. Since these nitrogens are apart from one carbon atom, so these are the position where we can have the lithium. But here we can have only 1 lithium because of the close proximity of the nitrogen. So if I put again here lithium with this lithium and this lithium will repel each other. So as a result, we can end up with 1 lithium. So after having this geometry, we can always, here is some data. I'm not going to the details. So you can see here, the 1 lithium can take up to 5 hydrogen, whereas 2 lithium can take up to 10 hydrogen. So in that way, we can tune the gradual absorption of the hydrogen in a single organic moiety. So these are the geometry of that lithiated complex along with the hydrogen molecule. We have performed the same experiment, and to see whether the binding energy is going to the Fischer-Tropsch mode or the chemi-Tropsch mode. Most of the cases we found they are in the Fischer-Tropsch mode. So to prove our data, we took different theoretical models, because I am a computational chemist, so I need to find the value more accurate to the experimental value. So we did several methods to calculate the binding energy, and for most of the cases we see the binding energy lies in the Fischer-Tropsch range. So these are the comparative study with respect to the gravimetric weight percentage. You can see the pyridazine, it has 6.45. If I this with the sodium, it is 10.42. With the potassium is 11.84. But you can see you can change the lithium to sodium to potassium. We can have large gravimetric weight percentage, and these are also quite good results in terms of the hydrogen storage. So we are hoping the experimentalist can synthesize these systems and we can have a good energy storage, hydrogen storage material. So as a chemist, so I need to understand that what actually going on. Here, this is the electron density map of that particular lithiated complex to see whether the Fischer-Tropsch mode is correctly operated or not. So we have plotted the electron density, the peaks as associated with the electron density region. As you can see, there is no such bond between this is the hydrogen, this is the lithium, and there is no such bond between lithium and hydrogen, or rather than a long range electrostatic energy term. So that means the hydrogen molecule is attached with lithium with a long range interaction, so the Fischer-Tropsch nature is restored. So whenever we have the necessity, we can remove the hydrogen molecule easily. Okay, so these are the temperature effect, because in the thermodynamics we know that the Gibbs free energy should be negative for a spontaneous reaction. So we do different temperature calculation, and we can see from in the room temperature the absorption is not the exothermic in nature, whereas the low temperature that all the reactions or all the hydrogen absorption process is exothermic in nature. So by which one can understand that what is the optimum temperature for the hydrogen storage in particular organic systems. Okay, this is some oxadiazole based hydrogen storage building block. Here the beauty of this system is that we have two heteroatoms, one is oxygen and nitrogen, but we initially expect that the oxygen also binds nitrogen, but we ended up with the lithium bind with the nitrogen molecule, again as the previous cases. So these are the building blocks, and here these building blocks also can absorb the hydrogen molecules quite efficiently. You can see here, this is oxadiazole complex. One lithium can take up to 5 hydrogen molecules. Then every time we can see, even if I change the organic moiety, well, the lithium can take up to 5 hydrogen molecules. What is the reason behind that? The reason that when this lithium is bind with the nitrogen, we know there is a charge separation, and the nitrogen is more negative and the lithium will be more positive. So once this positive ion, they are making a dipole-dipole interaction with the hydrogen molecule. So that particular interaction keep the hydrogen in the molecular form and absorb on the top of the lithium. So lithium can take up to 5. If I put 6 hydrogen, then lithium cannot take. So most of the cases, single lithium can take up to 5 hydrogens, and if I have the 2 lithium molecule, then I can have 10 number of hydrogen molecules absorbed on that particular moiety. Okay. Okay. Here also we have shown the binding energy. So I hope this data is visible. These are the different level of computation we did, and for all the cases we can see as we move from the number of hydrogen, the binding energy is gradually decreasing. That means the lithium can take up to the 2 lithium can take up to the 10 number of hydrogen molecules, and beyond that it will not going to bind, and the binding energy will be positive. Okay. So negative binding energy means the absorption is feasible, and the binding energy range in this particular region, this minus 0.6 to minus 0.2 electron volt, is the physics-absorption nature. So here also we have plotted the average delocalization correction energy versus the number of hydrogen molecule. All the calculation we need to do just because to ensure that whatever we are getting the trapped hydrogen on the lithium, that is going to be stable or not. So from here we can see all the hydrogen absorption process is quite feasible. And as per the gravimetric weight percentage is concerned, all these above 10, which is pretty good result as far as the Department of Atomic Energy, US Department of Atomic Energy hydrogen storage material gravimetric weight percentage criteria. Okay, these are some bonding nature. This is quite same. And here also we have done some temperature effect, and here also we see that most of the time if I increase the temperature, then you can see the Gibbs free energy is going to be in the positive direction. So that means the spontaneity of the hydrogen storage is lost. Okay. This is sulfur based system. So here also the nitrogen is the only heteroatom that can bind hydrogen, and here also we can have, see here also the lithium can up to 5 hydrogens. Beyond that, this one lithium cannot take 5 hydrogen molecules. So here also all the systems can trap a good number of hydrogen molecules, and this is the average absorption energy, and all these very pretty much close to the physics-absorption criteria. The same calculation we have done. If you see here, the gravimetric weight percentage is little bit low for this 1, 2, 3 thiazole complex, but for the 2 lithium class, this is beyond 15 weight percentage. So if I can consider only 1 lithium, then I can say that oxadiazole complex is far better acting as a hydrogen storage material than the sulfur-based system. So here also we have done the similar temperature effect, and the results are same. Now we actually move to some coinage metal system to see whether they can also trap the hydrogen or not. So here we have used the silver, gold, copper. So one can ask that why gold, silver, those are pretty much costly element. So why you are using that? But if I am concerning about my weight percentage in the materials, we can take those system and can see whether these has any advantage over the alkali earth metal. So here gradually you can see we have doped 1 silver and gradual hydrogen storage, 1, 2, then 3, then 4, then 5. So 1 silver can take up to the 5 hydrogen molecules. Gold, the same. 1 gold can take up to 5 hydrogen. Copper also can take up to 5 hydrogen molecules. And these are the 5 hydrogenated coinage metal based organic system. And we have here you can see the weight percentage of 5 hydrogen molecules is pretty much close to the minimum weight percentage required for a material to be acting as a good hydrogen storage material. So these are the work we have performed in our laboratory, and we are collaborating with the experimentalist to see whether that these materials can be synthesized. And there are a lot of other works also going on the hydrogen storage material, like fullerene, calcium borohydride, ammonia boron complex. Those can also be acting as a hydrogen storage material. So the work will go on, and we hope we can have a good energy storage material that can efficiently store hydrogen and in a reversible manner, so that we can use that hydrogen whenever it's necessary. So coming to the second part, which is based on the lithium-ion battery. So before going to the lithium-ion battery, I like to discuss a little bit about what is exactly happening inside the lithium-ion battery. And most of the cases, if we see the lithium-ion battery, you can have the electrolytes as a lithium salt. So the electrolytes that uses in the lithium-ion battery, that basically like LiPF6, like LiBH4 or LiBF4, those kinds of salts are using as an electrolyte in the lithium-ion battery. So here you can see the role of electrolyte is to transport the lithium from the cathode to anode. So it has a very, very significant role in the lithium-ion conduction. So lithium PF6, if I talking about, it will be dissociated as lithium plus and PF6 minus. So we are thinking to develop some electrolyte salt that can efficiently serve as an electrolyte. So look at this anion. This is PF6. So this anion has a special characteristics. We all know if I take only phosphorus, this PF5 is a stable compound. If we want to add extra fluorine atom, then we need one extra negative charge. So that extra negative charge makes the PF6 the high electron affinity, and the electron affinity is more than the chlorine atom. So we termed those systems having electron affinity more than chlorine atom, that can be termed as a superhalogen. So our idea is to develop this lithium-ion battery with the help of the superhalogens anionic part. Okay. So this is the basic working principle in lithium-ion battery. We can have the cathode, which is basically the oxide, lithium oxide, and this is anode, basically the carbon-based material or graphite, and there inside there will be an electrolyte, and that when we are charging the lithium-ion battery, the lithium is moving from cathode and it's stored at the anode, and while it is discharging, the lithium gradually move from the anode towards the cathode. So during this lithium-ion conduction, we can have that energy. So these are the common electrolytes used in the lithium-ion battery. But this has certain disadvantages. Like you can see, all these systems is like the halogen containing systems. So that means in terms of toxicity, we can see the halogen-based complex has some toxicity. So it is better not to use the toxic material in the lithium-ion battery. So we are thinking to generate the electrolyte which is halogen free. Also, if I take this lithium PF6, this lithium PF6 is very much toxic, as well as this PF6 readily dissociate as a PF5 and F minus. This F minus can bind with this lithium and form the lithium chloride. So the lithium ion conduction will be hampered if I am going to use lithium PF6. But still people are using lithium PF6 because it has some advantages along the current density. But we are thinking to find one electrolyte that can have better current electron density and also that will be halogen free. So to do that, we took several halogen free. First we tried the normal used electrolyte. These are the anions like BF4, PF6, arsenic fluoride, then ClO4. How much binding energy is there when they are binds with lithium? Then we can have some kind of understanding that if I am going to develop some kind of material, that same binding energy can be restored. So look at this binding energy here. This binding energy is ranges from 7 electron volt to 5 electron volt. So this is the optimum binding energy, lithium binding energy in the lithium ion battery. So if this binding energy is large, then what will happen? Lithium will not going out in the solution as a lithium plus. And if the binding energy is very low, then also lithium will not make a salt in the electrolyte. So the thing is that the binding energy in the lithium in this electrolyte should have an optimum binding energy so that it can move very smoothly between the cathode and anode. Okay. So this is one criteria. Another criteria is the moisture, the affinity towards the moisture. So we have calculated the affinity with the water molecule, and we can see the binding energy of the electrolyte salt should be based on this 1 electron volt. So this binding energy of with water molecule is reasonably good, and we can say that if we can produce some kind of material that can have this binding energy region and this binding energy with water, we can say that that can be also used as a electrolyte. Okay, so to do that, we first develop this system. This is we have developed from the boron system. This is B12H12 2 minus. We know this is a chloroboron. And if I can replace this one boron by one carbon, then we can have CB11H12 minus. So this we can say this is a carboron complex. First, we wanted to see whether this carboron complex has the similar binding energy with the lithium or not. So the salt they produced will be lithium CB11H12. This will be the lithium carboron system that we are thinking to serve as an electrolyte. So here you can see the value. The binding energy value is 5.08 electron volt. So this is in the range that previously those electrolytes we are using. This is the range 5.5 to 7 electron volt. So we can say that in terms of lithium binding energy, the carboron system can efficiently be used as an electrolyte. So then the next thing we need to see the water affinity. So we have calculated and we see this is more or less 1 electron volt. So the binding energy criteria and the water affinity criteria, they are quite matching well with the traditionally used electrolyte in lithium ion battery. So we proposed this, and That time we proposed this in 2014, and that time the Toyota group in the US, they have synthesized this complex, and they showed that this particular complex, they are actually very efficient electrolyte rather than the traditional electrolyte those were using in the lithium ion battery. And they further produced the magnesium carbon complex whole 2, and they used this magnesium ion battery for the car industry. So whatever we have predicted that carbon system or lithium carbon can act as a good electrolyte, they can be actually synthetically available, and more in Toyota group of industry, they are actually using the magnesium carbon in the car industry. Now look at this carbon system. This is the inorganic molecule. So we wanted to see whether some organic systems can also do the same thing like the inorganic carbon system. So we have taken, these are the heterocyclic system, and these systems are also used as a hydrogen storage building block. We used this as an electrolyte also. Now we have substituted this hydrogen with that NO2, and we can efficiently see the binding energy of the lithium is quite good in comparison to the carbon system. So here I have shown these are the inorganic system, and these are what we have, these are the organic system. So the binding energy is pretty much close, and since organic molecule is more soluble in organic solvent, then we can say these organic systems are pretty much useful for the electrolyte in lithium ion battery. So one can ask that so many NO2 that can cause some kind of explosion, because nitrogen is NO2 is not a good species. But we checked that, and we can remove one or two NO2 group. Still, that particular NO2 group can efficiently work as a lithium ion battery electrolyte. So as I say, once we model something, we need to see whether that they are stable or not. We do the stability, and these are the parent moiety, and this is the lithiated complex, and we see the fluctuation. This fluctuation is not because of the energy difference due to the structural orientation, but rather than the movement of this NO2 group, because this NO2 group can freely rotate, and due to its rotation, this type of energy fluctuation is occurring. But during this 500 femtosecond trajectory, there is no structural distortion on the parent moiety. So we can say that these systems can be stable and can be used as a electrolyte in the lithium ion battery. So this is the electrolyte part. So now I am coming to the additive part. So there are two different ways you can actually enhance the efficiency of lithium ion battery, right? As I told earlier, that if I am going to use LiPF6, that is dissociated as Li plus and PF6 minus. That means, and I told this PF6 can readily dissociate to PF5 and F minus, and that F minus reacts with Li to have the LiF, which can hamper the lithium ion conduction, and also the lithium storage on the anode during the charging. So we need, if we can remove this PF6 by using some kind of anion trap material, so the lithium will be free. This is one way. And another way, we just remove this PF6 and use some different ion, so that they cannot form this type of LiF complex. So earlier I have shown the carbon that can be removed by this, that can be substituted by PF6. So lithium carborane can be used. Or if I am going to use the lithium PF6, then I have to have use some kind of additive so that the formation of lithium fluoride is prohibited. So experimentally, this species is used as an anion trap material. So if I use this system in electrolyte, what will happen? The boron site, this boron will capture this PF6 so that the PF6 will not further dissociate. So like this, they can form the bond. So once PF6 is trapped by this anion trapper, so lithium is free and we can have a good quality lithium ion battery. So use of additive is also very essential. Now we wanted to see whether we can actually develop some better anion trapping material rather than this traditionally used this particular complex. This is known as tris pentafluorophenyl complex and popularly known as TPAPB. So this TPAPB is used as an anion trapper in this LiPF6 and LiClO4 electrolyte. So first job, we need to see how their binding energy. What is their binding energy? So we see the PF6 binding energy is minus 3.16 kilocalorie per mole. And for the ClO4, this is minus 18. So if I have to produce some kind of material, we need to see or we need to look this binding energy. More the binding energy, more the efficiency, because this PF6 will not be removed from these complexes. So lithium plus ion will move very faster. So we have used these organic moieties. These are the organic moieties we have used. And we found the binding energy is really large in comparison to this TPAPB. This is minus 3.19. But if I am going to use our system, then the binding energy is quite large. So this is how they form the complex. So what is the reason behind their forming the complex? Because of the presence of this boron. We all know that boron has a vacant p orbital. So that means boron act as a Lewis acid. So if I am going to use this boron based compound, the efficiency of this boron towards the anion will be more. So here is one example how we can use the Lewis acid in the lithium ion battery also. As this boron is Lewis acid, so boron is positive center. So if I can increase the positive charge on over the boron, then the binding energy also will be pretty much increased. So what we did, we substitute this particular here the hydrogen by these two electron withdrawing group. This is cyano group and this is NO2 group. Once we add this cyano group here, this electron withdrawing nature of that group pulls the electron from the boron center, making the boron center further positive. So the interaction with the anion will be more. So we have checked the binding energy. You can see here, you can see the boron charge is 1.6 when I am using this complex. When I am using this sulfur based complex, the boron charge is 1.3. When I am using this boron complex, I have 1.41, because I can gradually increase the positive charge on boron center. So as
I am requesting to our respected participants, please take patience for a few minutes.
Uh,
A
a- a-
technique.
a- any issues?
Oh, I think no, sir. You can carry now.
Okay,
A
is the
technical
slide
problem.
okay? Okay, is the slide is visible?
No, sir. Your slide is not visible now.
Okay, okay, okay. So just because, okay, let me share it again.
Okay.
Okay, now I think it is visible.
Sir, it is visible now.
Okay, so you see in the lithium PF6, this is the initial initial time, and after some time, when we do the molecular dynamic simulation, we can see the lithium is clustering in the one position. Means that the lithium ion movement is hampered. But once we use the TPAPV as an anion trapper, this PF6, the lithium is now free, and the green, those are the PF6 ion, they are actually trapped by the anion trapper. So to further analyze, we have produced the G of R calculation, and you can see from the lithium PF6, if I am going to use our additive, which is like this is green in color, you can see the lithium is more close towards the PF6 to which suggests that the movement of PF6 is hampered. Here you can see the lithium is actually surrounded by the solvent molecule. So 5 solvent molecule can be surrounded by lithium. What will happen once you charge your battery? This whole complex is moving along the electrolyte and going towards the layer of the graphite, which is the anode, and then the the solvent molecule is discharged over there, and lithium is trapped on the anode. And so the solvent lithium system means this type of complex actually facilitate the lithium ion movement. So this is more feasible once the PF6 is removed from the electrolyte. So we do lot of calculations over there, and we can we after some after doing all this calculation, we predict that our model system can act in a better way than the traditionally used lithium and battery electrolyte additives. So this is the second part. Now little bit about the third part of my lecture, which is the small molecule activation. Here also we are activating the hydrogen like carbon dioxide, methane, and water. So here we are using simple acid-base chemistry, which is mainly Lewis acid-base chemistry. Normally, when we take one Lewis acid and Lewis base, they can form the complex like this. So because boron is electron deficient, nitrogen has a lone pair, they can donate. So we can have a Lewis acid base adduct. But think if this fluorine and all these hydrogen are replaced by a bulkier group. So then what will happen? There will be steric hindrance between the Lewis acid and Lewis base. So due to the acceptance nature of Lewis acid and the donation nature of the Lewis base, they want to make the bond, but due to the steric region, because of the presence of this bulkier group, they cannot make bond. So the frustration is generated in between this Lewis acid and Lewis base. So now, if I put anything inside this frustration, they will activate that molecule. This is the idea. And since for last couple of decades, people are working on designing the frustrated Lewis pair to activate the small molecule like hydrogen, water, or even people are thinking about to activate the nitrogen. So here we can do so many things. Like this is a Lewis acid. This is a Lewis base. So they can actually form a Lewis acid base pair. If I if I take this example, we can see the ligand is here C6F5. So this ligand has an electron affinity is around 3.6 electron volt. So as a result, this particular ligand can take the electron from this boron, making the boron center more positive and more reactive. So obviously, if I change this ligand by a more electronegative by the ligand having more electron affinity value, so my boron will be more reactive. So we can think about superhalogen. As I told earlier, that superhalogen are the species which have the higher electron affinity value than any other atom in the periodic table. So I can replace this particular ligand by superhalogen and we make the boron more reactive. So what we did the same thing. We replaced the C6F5 by this ligand, and we found that the boron is actually positively charged and they can form efficiently with the Lewis base. So this is the traditional FLP and this is our design system. We have checked first what is the optimum distance between these two centers. This is 4.16 angstrom, and here also we have 3.94, 4.03, 4.62, which is pretty much close or in a range in the traditional used frustrated Lewis pair. So we can efficiently design this frustrated Lewis pair. Now our job is to see whether these can efficiently activate the hydrogen or not. Okay, so this is the traditionally used FLP. This is the hydrogen molecule. We have calculated the activation energy for this hydrogen activation, which is 8.3 kilocalorie per mole, and the total reaction energy is minus 8.1 kilocalorie per mole. So anything below this activation energy barrier will be a good frustrated Lewis pair for the activation of hydrogen. So look at here. This is our design complex. Here this is the hydrogen molecule and we have calculated the activation energy barrier. This is only 6.2 kilocalorie per mole. So obviously, if I am going to use this FLP that can efficiently activate the hydrogen. So I have hydrogen molecule initially. Now I have two hydrogen atoms. So during this activation, we can generate lot of energies. Okay. So this is the cartoon diagram how this actually works. So this is the molecular hydrogen. First, it's make a reaction complex with the Lewis acid and base, and this is the transition state where you can see the two hydrogens start getting apart from each other, and in the product region, these two hydrogen molecules, these two hydrogen atoms are separated by each other and making some complex. So the traditional FLP, we can have 8.3 kilocalorie per mole activation energy. Our design complex is 6.2 kilocalorie per mole activation energy. So this is clearly observable that our design systems can efficiently activate the hydrogen. So here I have shown the activation of water molecule. So initially, this water molecule is sit inside this. This is the Lewis base and this is the Lewis acid. Now, first step, this water molecule binds with boron and to make this bond. So these are the intermediates. And then what will happen? One of the hydrogen atom is getting discharged from this OH. And eventually, I have OH here, I have H here. So I can efficiently split the hydrogen molecule into OH and H. Okay, so this is the two intermediate geometry. Here you can see these hydrogens are going out. So this hydrogen is 0.97 angstrom. This is 1.02. That means this hydrogen is start going out from the OH molecule. Okay, so to understand this reaction properly, we have done some calculation. This is based on density functional theory calculation, and to understand any reactions, actually we can calculate the electronic activity that is occurring during the course of the reaction. So if I can simply take one single step reaction, if this is the intrinsic reaction coordinate and if it is the electronic activity, then we can have this type of plot. So the negative peak is actually associated with the weakening of bond, and the positive peak is actually associated with the strengthening of bond or the formation of bond. So we actually wanted to look at this particular water activation process in terms of the electronic activity. Here, this J is concerned about the total electronic activity. So this black line, you can see the negative region. That means the bond weakening process is predominant, because the water is activating and the one hydrogen molecule atom is detaching from the water. So obviously the weakening process will be predominant. So that's why we predict that first hydrogen atom from the water molecule start going liberated. So for the second step also, we can see these are the negative peak. This is associated with the electronic transfer process between the water molecule and the Lewis acid and base. Okay, so this is how we can actually do the water activation as well as the hydrogen activation. So by three different ways we can have the renewable energy, like in the hydrogen storage, in the form of lithium-ion battery, and in the form of hydrogen activation or the water splitting. So this is what we do in our laboratory here in the Haldia Institute of Technology. We are working on these areas. So if anyone interested to work with us, they are always welcome. We will do the calculation together, and whatever I showed mostly done by Mrinal and Abhishek. So and Swapan did some FLP work, and the previous was done by Naresh and Rakesh and Subra. They are my lab members, and whatever we have performed the experiment in this high performance computational cluster, we call that this Krishna. So this is a supercomputer, and what mostly the calculation we have done in this supercomputer, and the financial support from the Department of Science and Technology and Science and Engineering Research Board, Government of India. And okay, so that's all. Thank you, and I will be happy to answer if there is any question.
Thank you, sir, for your very informative lecture. And for the participants, if you have any questions regarding this session, you may directly unmute your mic and ask Dr. Giri sir,
Yes.
or you can also write in the chat box. Participants, if you have any questions, you can directly ask. Okay, sir. Once again, thank you for joining with us. We are very honored you shared your valuable information with us. Hope we will get you in future if you perform any further programs.
Yeah, if anyone has questions, you just write an email to me. I think, and I will be happy to answer the question. If anyone interested to work with us, they are also welcome.
Okay, there is an opportunity from Giri sir. If anyone having any any interest on working with sir, he can directly approach. Okay, once again, thank you, sir.
Okay,
Uh,
thank you.
for, for, for the participants, there is a feedback form in the chat box. You have to fill the feedback form. Without filling the feedback form, we will not provide you the certificate. For each session, you have to fill the feedback form. Our next session will start from 1:30 p.m. We'll again start our next session, the last session, the sixth session of 3 days FDP from 1:30 p.m. See you then. Thank you.
Okay, good afternoon to everyone. Time and tide wait for none, and we have reached our end session. Everybody, thanks for your kind participation. In this session, our eminent speaker is Dr. Abhijit Bardhan sir. He is a honorable assistant professor of civil engineering department from Bharat Institute of Engineering and Technology in Hyderabad. And he earned his PhD degree in 2021 from National Institute of Technology, Jamshedpur, and he completed his MTech from NIT Patna. And he has a several work experience in different types of college. He worked as an assistant professor in Ramgarh Engineering College in Jharkhand, and he has many journals with some other respected persons. Apart from it, he has several books also. So we are heading towards our eminent speaker, sir. And over to you, sir. Now, sir, it's my request to come and speak some valuable words.
Sir, your voice is
Sir,
not audible, sir.
your sound is not coming.
No, sir, we don't have the-
Dear participant, please make presence. A technical error is occurred now. Please give me a few minutes. Sir, you are visible, but your audio is not coming. On behalf of our committee, I apologize to our participant in this group. A technical problem was occurred. I think it is going to solve now.
Sir, I'm audible.
Yes, sir. You are audible and visible also.
Okay, sir. So now I can present.
Yes, sir. You can start your presentation.
Okay, sir. So, my topic, I'm going to give this presentation on renewable energy resources. So, this is a perspective report. Why I'm telling perspective report because I want to discuss on mainly on what we are doing presently for renewable energy resources, different kind of methods. What already I think in past lecture what I have listened, Balram sir already discussed what the present basic problem we are facing and what is the procedure we are adopting in present situation. And in third lecture, second lecture I have in lecture I have seen Sopan sir already discussed about Tata Power project, whatever renewable energy they are doing, and in last lecture what I heard from Tanmay sir, there also get some information. So I'm going to avoid the main basic things, and I'm going to discuss about the future prospect. What is going to need to adopt in renewable energy resources that we are going to discuss here. So immediately we'll go to our slide without any time consuming. So then what are the natural basic things? What are the natural resources? The natural resources are the means what we are using daily. Water is coming from nature, earth, mother earth. That is we are calling as natural resources. The material we are consuming like like as a fossil fuels or we are water, plant, animals, or any biomass energy we are consuming, or wind or solar radiation we are grabbing. That is we are calling as natural resources. And different types are there, so we will discuss later on that. So basically we are two types, they are natural resources. One is for renewable energy resources and one is non-renewable energy resources. Renewable means what will be coming every time as a new process. It will be kind of not endless process. And non-renewable means what we are a particular storage is there. So that storage can be finished within a particular time. So that is we are calling as non-renewable energy resources. Definitely this presently we all government from in each and every country, basically US and Japan and Indonesia has involved much more. And we are the fourth, India is the fourth country which is giving importance to more on non-renewable to renewable. In 2010 we have started so many project, solar panel project, and this wind project. So non-renewable energy resources are the resources which are basically come from endless process, like wind energy and solar panel energy, solar energy, hydropower energy, biomass energy, like this kind of thing. What is non-renewable resources? Non-renewable resources defines which is comes from a limited source, means finite source it called. Yeah, like fossil fuel, gas, natural gas is what we are presently using, and coal obviously that is also come from fossil kind of material, and oil, natural oil what we are using. So what is basically defined by the RSR, renewable energy resources, defined by wire and towed oil, and that is they defined as energy that obtained from continuous or repetitive currents, means present flow of energy recurring from the natural environment, means they which will not going to be an end. That is the main definition. So similarly from uh, source and ATL also defined the same, and we have collected from the basic definition of which is defined as renewable energy is that collected from renewable sources, which is not going to be it, which is naturally replenished on a human time scale, such as sunlight, wind, rain, tides, tidal waves, means tidal energy condition, energy we get, and geothermal heat that also comes under renewable energy resources. So types of renewable energy resources. What are the different types? Means renewable energy resources we are getting. Renewable energy resources means energy that are sustainable, which is going to cannot run out with the time. Like solar, hydropower, wind, and geothermal, tidal, obviously, and biomass. We are going to discuss about this kind of point. Mainly, I'm going to discuss on solar and solar, hydropower, and wind project. What are change we are going to, we need to adopt for near future, means up to 2040. So, what is solar energy? Solar means where according to sunlight and solar radiation, we are getting that energy and converting it to our usable energy. Like we are solar cooker is there, solar panel from a solar water heater is there. So we are using that as a solar energy. So that is basically we used to see that some panels in means home remedial uses. We used to use that panel should be inclined, means approximately for 30 to 45-degree incline. But in power plant cases, we can see that that panel will be mostly in a vertical condition, means horizontal condition. So, horizontal. What is the difference between those two? We will discuss this later. Next, hydropower. We have already discussed that hydropower is, we have seen that Tata Power project when Swapnin sir has discussed, he has already mentioned that flowing of water, we are resisting it, and we are creating hydroelectric power through dam project. That is, we are coming as a renewable energy resources. Next, wind power. Means wind tunnel, wind turbine we are keeping. So that is giving our energy that is coming from wind power. That is kind of infinite energy because it is wind is flowing and sun is coming. So that is kind of a wind energy power. Next is tidal power. Means we are getting energy from tidal condition, means tidal, whatever tidal flow is there, wave formation, and we are putting turbine to get that energy, consuming that energy, converting to our consuming with our storage, and that we are using as a tidal energy. Next, geothermal energy. Geothermal energy power, that is from geothermal means from we are using some conduction we are getting from ground. What is geothermal means ground core, earth core temperature we are consuming and we are using in our home remedies or in any power project, and we are sending that cold temperature means lesser temperature here heat whatever it is, and we are sending back to the earth. That is geothermal power energy. Next is biomass energy. Biomass is carbon uh, flavor energy. That is, we can say that carbon natural electric generated from a renewable organic waste that we used to dump in dump yard or in land simply, and it used to give bad smell. So we are using to create a renewable energy that will be useful for the society. So that's kind of all energy we are consuming. So mainly my will come to our main project, that is hydropower generation and its perspective for future renewable energy generation. So what are the perspective of uh, hydropower generation at present and in future, and what will be the what will be the challenges that in engineer is going to face, and all the project scientist is going to face, that we will discuss here. So hydropower we have seen already in so many studies, and that it is to from earthen dam or gravity dam or whatever it is to flow that water in high speed, and one turbine will be there. As we can see that a turbine will move, so that will create a head. After the based on that head we will create this hydropower. So next, these are the hydropower plants in India where we have seen, we know all this, where all hydropower energy is there. So next is the microcrystalline perspective of hydropower generation. What are the hydropower microcrystalline features? Means which will be useful for future hydropower generation as a renewable energy resource. That are the hydrological modeling setup for that particular river basin point, and that zonal condition. Or second is discharge, means river flow discharge, means its melt contribution, or how much water availability water is coming as a surface runoff, or it is counted as a base flow, or it is coming as groundwater availability condition, that we will count in here. Because this melt condition, it's going to contribute continuously, it's going to change. We will see some figures that snow melt what is contributing in say in Himalayan river basins as a surface runoff to the river point, particular river point, that is going to change by decadal condition. Whatever in 1976 so it was there, some value it is changing to some percentage, reducing or increasing in present condition, and we are projecting with that with up to 2040 what will be the change in the percentage in water availability and melt contribution. That is the second point. Third point is that hydropower potential estimation. With hydropower potential, we can build that, or we can increase the capacity of that particular hydropower project based on its high flow condition. Its flow condition means how much when this head will be available, how much head available, with how much head availability we can build the hydropower project in that particular area or zone. We can see the grid later. We can see that how much low flow condition is going to occur in present situation, what is the low flow condition, and in future how much low flow is going to occur, and what is the maximum flow condition to maintain that barrage or where or whatever we are using dam purposes. That is the third point. And potential location identification means where we can, if we basically this point is basically for planning of hydropower project, means which position will be suitable for hydropower generation in a particular river basin, means which point is going to we are going to select based on its head, its availability, flow availability, based on its uh, obviously soil condition and site suitability, like that. And say next point is site suitability with the help of hydropower potential. Means site suitability means in we can we finally after recognition survey and all other location identification, we can find out 3 or 4 points. Then we used to select one point at a time that we are going to select for hydropower generation, that we are going to build a hydropower project based on the hydropower potential what we have discussed on this all these points. Based on that, and what is next point, what will be the impact on the environment based on this hydropower potential development at that particular position. We need to calculate that, means what will be the uh, basic effect to the our nature, mother nature, that we are going to calculate. And adaptation strategies also we are going to develop for it. What if any drawbacks will come, to say that will be adjusted for that particular project. Next, mitigation and minimization means whatever, just last point we have discussed, that adaptation strategies we are going to adopt for this environmental impact condition, that we are going to mitigate and minimize the shortcomings whatever is coming, that we are going to minimize in this kind of project. Mm, Next, so first point, we are here at hydrological model setup and development. So next we are so that based on that we are going to discuss about hydrological model, how it used to perform, whatever. First we need to check the ground condition. Ground condition means at the first point we have discussed what the hydrological model setup and performance. So that we are going to check how much we are accurate to generate hydropower, and how much accuracy will come for mm, our modeling purposes. We are going to project this renewable energy, we are going to project for at least 30 to 40 years. So we need to check the ground condition, means whatever flow is there, whatever how much flow is going to come in the future, and what is the soil moisture availability in that condition. All those we need to check for hydrological modeling purpose. So we can see that this is a case study we have did for Suvarnareka, and some study we have did for Satluj River Basin also. So we can see that. So here we can see model performance whenever is greater than means hydrological model performance. Here this in calibration and validation period we are checking. So all means in calibration, the model efficiency, when it will be better, then we go for validation. Means whenever model can predict any kind of abrupt situation, then we are going for validation period. Based on that, we are going to, based on these two results, calibration and validation, we are going to project the future aspect. So based on that, we have to project the what are the available condition available in hydropower project. We have to discuss about that. So we are here, we have in calibration and validation, we can see in daily, monthly time step we have analyzed for monthly, where monthly it is coming very good, means 0.98 to 0.94 in validation, and in ACNS hard clip efficiency it is coming 0.97 in calibration, and in validation it is 0.94. Wherever this R square is coming 0.84 to 0.76, means like it is some abruptness is involved in that. Why? Because we can see that in daily flow condition, some abrupt situation will be there, like a flash flood event, like our Kedarnath issues is when it came, it washed out within few hours, means 1.5 hour. So this kind of situation will be there in daily cases. So in daily cases, so abruptness will be there. In monthly cases, this will be averaged. Because of that, some smoothening curve will come, so that will match with the observed one. So because of that, we are getting better efficiency in monthly condition. So for this cause, those scientists, means whatever, whoever is designing this hydropower project, they used to take the abrupt condition. They have to consider the daily, means also hourly cases, like means this, in this case we can see they will consider this R square 84 and in validation 76, and based on that they have to take factor of safety, and based on that they will design the project. So here what free bias is denoting means percentage error, means what I have projected. You can see this figure. We can see that best observation is red color, and this green color line is observed values. And we have projected some uncertainty band condition, that is 95 PPU, means 5% I have taken significance, 95% confidence level, 5% significant error I have allowed. So I have developed a band, like within this band all the uncertainty value can lie, means whatever observed and whatever predicted value based on my calculation. So we can estimate based on that. Means this 5% is nothing but null hypothesis testing. Means we know in probability null hypothesis means means when each zero value will be less than 5, so we are considering that curve, and 2.5 left side and 2.5 right side condition we are taking, that is combined as an 5%, and that remaining 5% is confidence level, 95% confidence level we are allowing for that. Next, that is null hypothesis testing. Next, p bias. P bias is percentage bias I'm allowing, means how much we can see the deviation, means from main means observe point means blue color, and whatever is I have projected, means we have projected in our project, that's Subarnarekha project. So that is the red color. That is in most of the cases we can see it is closely matching, and in some peak means flash event also we can predict accurately, but in some cases we are lagging in this kind of situation. So in that kind of cases we are getting p bias. Percentage bias means how much our observed value is differing from our simulated value. So if it is positive, that we are underestimating, means our observed value is more higher than predicted value. If it is negative, then we have overestimated, then we have to reduce our ground condition, means soil moisture availability or whatever it is. So like that, we are estimating this p bias, because all this why I am discussing all in developing a hydrological model for future aspect, and for which will be later useful for renewable energy resources estimation, and for that power project generation. This will be discussed, and this will be estimated. Next is RSR, means RMSE factor we know. So RSR means RMSE values, root mean square error divided by its standard error. So that we need to calculate how far it is deviating, and this p factor means how much percentage it is covered, this observed and simulated value is covered by this project, what we have predicted uncertainty band, means this green color band, how much it is covered by most of the band. Next is R factor. R factor means uncertainty, or uncertainty involvement, that is discussed by R factor, and it denote by the thickness of the uncertainty band. This blue color band thickness, it is to discuss about that. This point we need to calculate for hydrological model setup for the present and for the future aspect. Means if you are going to project this scenario, means project for up to 2040, means the end of the near century period, means we are obviously we are in the presently, we are thinking that we are in the present situation. History, we are considering 1976 to 2005, and 2006 to up to 2020 we are considering as present scenario. Next we are considering from 2021 to 2040 as a near period. And next 2041 to 2070 as a mid century, upcoming mid century, obviously. And next is the end century from 71 to 2090. So this kind of point we are going to discuss. So these are the flow condition, means whatever we have seen in this point is discharge melt condition. Right now I think it came. Discharge contribution means as a melt contribution and its general water availability in the river basin. So we'll go to that point. So this is the flow condition of Satluj river basin. So they, in that case, when base flow is 0, means we are not considering this snow melt condition. Melt contribution, we are not considering this point. So that time, whatever discharge we are getting, and when we are adding this snow melt, so how much flow we are getting, we are discussing about that point. So when base flow, I think it hasn't came, it came. So when base flow is 0, this flow contribution is 0, we can see the deviation. We are not considering the snow melt at Satluj river basin. So we are not considering this. We can see this calibrated, means what we have simulated this value. And for 1981 to 2000, April 2000, we have simulated for our present scenario, because already we have the one hydropower project here. One already just
মনোরঞ্জন সাহু স্যার, মনোরঞ্জন সাহু স্যার।
So base flow contribution we are we have added. So whenever we are calculating, means we are adding snow melt based on snow depth. Snow, how much snow depth is there, we are getting based on the GPS coordinate system. GPS, we are adopting GPS system from NASA satellite data set. That depth we are calculating how much depth is there. So generally that snow melt contribution will be up to 1 meter of that melt snow depth. So that coverage, area coverage, we are knowing by that GIS technique we are mapping. So how much area coverage is there for land, if you download some Landsat map, so area coverage of that snow melt area we can get, and we are multiplying that depth, we have say 1 meter. Then we are melting condition, melting temperature we need to fix according to the ground condition. Means whenever in 4 degree it is melting, yeah, it is 2 degrees. Sometimes based on the coefficient it used to depend, sometimes it goes to 3 degree, sometimes it used to melt at means 4 degree also. So and whenever this in cold season, and we can see this contribution will be less, and in summer season we can see contribution will be more. So that kind of situation we need to have, adopt. When we are adding this base flow contribution, we can see this is first step, and this is the this when base flow we are adding, when melt contribution we are adding 65%. We can see the perfect matching in between this base flow 65 condition and base flow 0 condition. Whenever this base flow means snow melt contribution is added to that particular basin, so we are getting particular means behavior of that river basin. So based on that, we are going to project the future flow. This based on this, we have calibrated this value. So we are going to, based on this projection system, we are going to project for future scenarios. Means we are going to project up to 2040. Whatever present that hydropower project is there, and we are going to increase that its hydropower generation values, or we are going to adopt, we are going to carry forward for that whatever new hydropower generation they are developing that 5 kilometer forward to that point, Bakranangal Dam. That we are going to discuss. So next point is that low flow analysis. What is that? These are the general average flow condition we have seen here. This we will discuss about the low flow condition. Means most except this few river basin in India, means like whatever snow melt contribution is there, all are perennial and perennial river basin. So we need to consider this low flow condition. Means whenever low flow will occur, we can generate the hydropower project or not. We know how much low flow will occur, and we need to store that water based on to generate the flow, means hydropower project for particular time. So for that reason, we need to analyze the low flow condition. So this we have seen this figure. We can see that here low flow we have analyzed. This is for RCP, means representative concentration pathways. Means we are going for future scenario. Just before 10 minutes, what I have told, that we are dividing in a few decadal years. Means considering few decadal years, means from 1976 to 2005 we are considering as historical period. Next 2006 to 2020 we are considering as present scenario. Next 2000, means here I am 14 because there I have considered up to 2040 we are considering near future period. Then next from 41 to 2070 we are considering mid period. So like that, next is up to 2100, means 2021. We are considering end period. So we are going to up to its lifespan, we are considering up to 2040. So based on that, we need to analyze the upcoming future low flow, what is going to come to our river basin, whatever in Suvarnarekha they are trying to develop one barrage and do one dam near to Ghatsila. So that we need to analyze the low flow, and similarly like, but we are not discussing about this here about low flow of this Satluj, because Satluj is already, we have seen this point that Satluj is snow melt contribution is much more higher. So in Satluj we no need to consider this kind of low flow condition. No need to consider. So for this cause, this low flow condition we will analyze for hydropower project generation for those river which is not feeded up with snow melt contribution. So this low flow analysis we are going to discuss about low flow can be analyzed by two process. Means cumulative days, number of cumulative days low flow is going to consider. Means we are using 7Q10. 7Q10 means we can see that minimum 7-day flow that will be reoccurred within 10 years, means as a decadal year. So is not 10 years, we are considering as a decade. So that decadal year, 7 days minimum low flow we are going to consider. So here also, here I have shown this for 7 days. Here in our project, we are estimating for 30 days, 30 days low flow, 30 Q10 also we used to consider. Then 60 Q10 also we used to consider. Means we are trying to evaluate the minimum flow condition. Based on that, we need to store our flow in that particular time period in the future scenarios. So for this cause, we need to, based on this condition only, we are going to giving report to the government. So they are going to take care about those points for this particular hydropower project. So here you can see with that low flow condition for this red color is for present scenario. You can see baseline means 0 line I have kept in our present scenario, and in all other conditions means projected scenario means up to 2040 whatever it is going for this RCP 8.5 and RCP 4.5 scenario, they are going to reduce, means low flow is going to reduce. So what will happen for that? So we need to store more water compared to present scenarios. If presently what we are conserving the flow, in future in summer season we need to conserve more flow for the power generation in the summer period. That is the point. So what is the RCP 4.5 and 8.5? RCP 4.5 is the representative concentration pathways, and RCP 8.5 is the representative concentration pathways when carbon concentration is going to increase up to 850 mm per meter square. So that's kind of two scenarios we can see in when in end session we discuss about that. We'll go to the website. So how to estimate that. So these two scenarios, there are four scenarios, but why these two scenarios I am considering that I'm considering as a band, like if you'll go to the previous slide, means like 5% here I have taken 5% PPU band. So maximum and minimum band means lower point and upper point I am considering. So for this course I am taking 450 emission scenarios, carbon emission scenarios, and 850 carbon emission scenarios. Based on that, I am going to choose all those material, means whatever low flow is going to occur in that summer season or whatever it is. Then we need to, based on this, we need to conserve the flow. Next, we need to analyze the high flow also, because based on head and overtopping condition also we need to consider this point. These are the flow condition of river Subarnarekha for a proposed hydropower project. We are developing for near to Ghatsila. We are familiar with the Subarnarekha river basin. These are the high flow frequency curve, means when 1 day maximum 1 day flow condition we have considered. Then 7 day means cumulative 7 day. If we'll go to the previous slide, we can see 7 days low flow. Here we are considering with recurrence interval. Here we are not considering with recurrence interval, because in high flow condition that will be cumulated. So we no need to consider for the recurrence interval. In low flow condition, we need to consider this recurrence interval. So in 30 day, 60 day, and 90 day low high flow condition and its frequency, we have estimated whatever the maximum flow will come. So based on that, we need to design our dam project, whatever is going to consider, and for the hydropower project. Next, low flow frequency curve, that for that similar whatever is we have developed for 1 day, 7 day we have seen that flow frequency. Similarly for 1 day, 30 day, and 60 day we have developed. Means how much flow, means if it is considering low flow, so we can see this in Subarnarekha river suffer in future, that like flow condition will be occur. So we need to take care about that dam storage, reservoir storage. We need to generate hydropower project. Second point is consecutive low flow days, consecutive days of low flow. Why we are going to consider this point? Because in one day some low flow will come and gather in the reservoir. Next day we will see that in next day some flow will come and gather in the reservoir. So we need to consider all the flow condition, and then we need to flow it for reservoir for hydropower generation. For this cause we used to in hydropower project development we used to consider consecutive low flow days, and we need to develop this cumulative days, how much for 2 years how much low flow will come in interval. In 5 years means upcoming means from 2021 to 2023 how much low flow will come, and from 2020 for 5 years 2020 to 20 means what 2026 or 25 how much low flow will come, and after 2030 like that. So we need to develop this low flow condition. Why it is maximum for 2 years of interval means consecutive days low flow will accumulate each other. So each and every data has 2 years interval. So number of data is there. So that will be accumulated for particular value of low flow. So that will be accumulated in a particular 2 years condition. Number of data will be more. Means in up to if you're considering we have considered after 2040. So here we will see how much means 2021 we have get 10 value. In this kind of cases we will get less value. So we will put some it is coming very less. So next point. So all the points, if you go to the first slide, here we have discussed up to low flow and high flow condition and head availability, potential location identification means whatever wherever this location will be perfect. Means if you go back to this from this PPT mode, and if we will open this, this is grid set we are developing for river basins. This we are taking in means upstream point of Suvarnareka river basin, and this the end point we have taken here about near about Ghatsila river basin, Ghatsila point. This one. So this is the digital elevation model we have developed. We have taken from USGS dataset. So we are developing some flow net, so where we can properly in which place will be suitable for river means that hydropower project we are going to develop that. This point we can see this up to maximum extent. Here we can see how flow is varying. If you will put on a this depth curve, is the water WAC means water surface normal elevation, and this is the depth of water in a average depth of channel. We can see that. So if you run this model, we can see how much variability is going to come in this. So we'll just minimize little bit. So how much in flow we are getting, and this we can see this will be running. So time it is running. So this depth is going to vary. in some point it is increasing. This flow point was not there. So like this, if you increase this kind of water wherever is consume, it is coming maximum. So we'll pause that. So in that situation, if you scroll this value, it is going to flooded this point. It is going to with time. It is going to reduce. Again, it is flood is going to come. So it used to, if you draw this point, again it used to going to increase. So in this kind of cases, we can see this if we have taken depth condition and how much depth of flow we can see with this point, that how much depth in the above the mean water level we can see this flow variation. And this is the first point of choosing the wherever which point site will be suitable, means in for this hydropower project in between Subarnarekha in Subarnarekha river basin from Jamshedpur to Ghatsila. Based on this kind of flow grid net, we used to select this point, and we can see this flow condition and the geometry, geomorphometry, how it is going to change, how it, where in upcoming 10 years we are going to propose this project. So which point will be degraded, means which bank will be degraded, we can see based on the ground condition, geomorphometric condition. If we zoom this point, so based on that, we are going to select, we will select this flow point. So which point is going to hit flow direction. So this point after few 5 years, so this point will be most of the cases, it will be this point will be raised. So some portion will be degraded. So if we are choosing this point, so we need to take care about this kind of position. So this is geomorphometrical analysis we need to do for that particular point, and we need to develop hypsometric curve for that point. So for that particular grid, means I am taking this grid, if I am taking this grid boxes, each and every grid boxes we have divided. So if I am going to take this grid, I need to develop one hypsometric curve for that. So based on that hypsometric curve, we can consider this condition. Okay. Next point. Next point is perspective of solar power generation. Solar power, in solar power generation, whatever problem we are going to face for this development of RSR, means renewable energy resources. And in India only, mainly we will discuss about Indian solar power generation and its future aspect, and whatever problem we are going to face for that, we are going to discuss that. So generally we know how the solar power used to generate already. So many speakers have discussed about it. So how the sunlight is come, solar panel will be there. So small, very small solar cell will be there. That will consume that solar radiation will come, that will be stored in battery and will come for use. So next. Next point is that solar in solar power plant. This is for home use, and this is for solar power plant. Similar, like we can see that inclined. That point that time I have told what is two types of solar panel. We can see one is inclined, one is for means near about horizontal. We can see. So why? Because in next slide. Yeah. In normal, in horizontal solar power cases, we used to calculate this solar power calculation using this formula provided by one US engineers, that is E is equal to ARH multiplied by PR, where E is the energy, solar energy, per means kilowatt hour, and A is the area of that panel. R is the solar radiation yield, and H is the annual average solar radiation on that title panel, and means average condition of all 365 days, and fear is the performance ratio, and that is means coefficient, means constant, means it varies from, in some cases it varies from 0.5, 0.6, 0.9, like that. In general default cases we used to take PR is equal to 0.75. So in that cases, we used to consider in horizontal cases when plane will be there. So we used to consider this formula. When vertical case will be there, means it is a little bit inclined. In that case, we will use uh, PA. I is equal to total solar insulation. I is equal to S cos theta. This point means is cos theta means cos z means here where it is zenith angle, means how much in inclined plane it is going to come and fall on the panel surface. So how much angle it is considering, we are considering this angle z, we are considering from the vertical axis towards how much, how far this solar radiation is coming and falling in the inclined plane surface. In inclined cases, we are going to consider this formula, and in this horizontal solar plane, we are going to consider this E is equal to ARHPR. So basically, based on these two, this is the difference between some plates will be means they used to keep horizontal, some plate they used to keep in inclined faces. So based on that, we used to consider this two condition. So what is the why? What is the drawback and what is the advantages of these two? Means in plane condition, we used to consider all the rays for based on the intensity, solar radiation intensity we can vary. But in inclined condition, we have so 2-3 boundary condition. Means when cos theta will be zero, means when that rays is inclined to the surface, so that time cos theta will be zero, value will be 1. So that time will be maximum. When cos 90 degree, it is vertically, so that time will be zero. So based on that condition, we used to consider this kind of solar insulation component. So we can see that in next slide, we can see this boundary condition, all we have written or whatever for the polar condition and for this um, yeah, that is what is the microcrystalline perspective of that solar panel. Means it has some boundary condition that in sunrise, when that it is obviously for inclined surface. First of all, that zenith angle, how much angle it is considering, means what we have seen, I is equal to S cos theta, that we are discussing. That zenith angle, that Z we are considering, Z is much more important, and solar radiation zone, how much, and each and every surface we can see that each and every grid box of our grid system is divided by, sometimes we used to divide 2.5 grid system is around 50. We have divided imaginary lines 50 kilometer by 50 kilometer, we are considering 2.5 grid scale. So based on that, solar radiation is to varies each from each and every places. That solar radiation zone to another grid cell we need to consider, and within the watershed where we are means, or within the panel member, within the area we need to consider. In case of inclination angle of solar plate, we need to consider this cases by cloud coverage. Means if it is cloud coverage is there, that intensity will be reduced. So that intensity we need to consider up to minimization of 10% cases. So that is allowable cases for according to USGS platform, which United States Geological Survey, whatever they have suggested. So 10% we need to allow this condition. This sunrise, when sunrise, just sun has rised, so that time we need to for solar panel energy consumption, we need to consider this formula is provided here. So 12 minus this. So I'm sorry for that. 115 degree and cos inverse sine phi and sine delta divided by cos phi cos delta. At third set, it is minus, means plus minus is 180. Just is varying inside and opposite side. So we will see the sinusoidal curve of cos theta. So we can understand this position. So one sinusoidal curve, so cos theta curve and sin theta curve we know. So when that cos theta curve is varies towards sunrise, when it is zero condition, and when it is going to means end up means 180 degree, that we are considering as a sunset point. So there's two condition we are considering here as a means based on the zenith angles. We are considering the solar radiation. Based on the solar radiation, we are calculating solar power based on the sun sign hour. So these are the formula we are going to adopt for inclined panels. Next we'll go for this one, this solar Indian solar map. This is the Indian solar maps. What we have is already there in so solar India. How this solar radiation is going to vary? It is obviously averaged map. So how kilowatt per meter square per day, how it is varying for each and every point. It is they have digitalized this point, and it is represented here. I have taken from map of India. Next, I am going to project this. Means what I am already I have told that we are going to discuss this point for future aspect. So we are developing some hydro means power project, solar. If we are going to project solar power project, so what is the condition we are going to face in the future? So this for that main component is solar radiation. So for this course, we have developed solar radiation, how much it is varying for future and for obviously for historical in 1976 to 2005. Next, we consider I haven't considered for here I haven't mapped for present scenario. This near future means up to 2040 we are considering near future and our project lifespan. Then we are going for, if it is we are going for long span 50-year validity or 60-year validity, then we need to consider for mid span. So here we can see this solar radiation SR. If you see little bit is this smaller, this legend SR kilowatt per hour per meter square per day. So how much in this Subarnarekha river basin, how much it was each and every cell, it is varying when it was 45 to 45.50, so to 57 maximum lowest point in that particular area. So it is going to increase by in near period. I mean 2014 to 40, it is going to increase 55 to 90, 55.95 to 57. Means it is it's general average value, minimum general average value is going to increase for this basin. So like that, when we are going for further mid span period, so it is going to increase little bit, but its lower value is decreasing. Means lower value means it in mid fan it was 55.95, but it in this case mid lower value is going to 54.75, but the higher value it was going after 2040 it would be 102, but in end century it is going to 116.38. So for solar power generation, we need to project this solar radiation vary, how much it will vary. So we are going to project this based on that. We are going to put our panels in which sub. These are the divided. We have divided grid boxes. So our sub basin we used to call. So this subbasin, which subbasin will be suitable for solar power generation, where we can put power plant, solar power plant, so we can get maximum radiation. Then we can go for hydro solar power generation. Next point. Next perspective is uh, wind power generation. Wind power generation perspective means it is we can see this wind power generation, how wind power we have already seen in so many lecture slides. So this wind power is coming, one blade will be there, two blades or three blades will be there. So based on its working condition, we used to this we know this flow of wind is a kinetic energy, and we developed a mechanical energy system, means that wind tunnel. So means that through that we are means energy conversion we are doing towards electrical energy that we are developing. So what is the main point means development of wind energy power potential is just we are from kinematic energy we are coming. So it will be energy will be half mv square. So half mv square by divided by t is time that we are dividing. So we are getting that formula. So based on that we can calculate our wind energy system. Here we can see this in some wind power panel. You can see that two blade will be there. In some cases, you can see three blade is there. In some cases, you can see four blade is there. So we'll discuss about those points. Yeah. Wind power calculation. You can see this forward wind movement. So V1 in this figure, V1 is flowing towards the panel, means wind tunnel. So it is going whenever it is floated up, it is going to increase its diameter because of its energy losses. So we can see this formula I have taken from one report of USGS based on how kinematic energy is going to convert to electrical energy. Based on that formula, we have seen. So we can see this how wind power velocity means is much more potential to wind power generation. Means when we are finally going to calculate it, wind power generation is the velocity is cubic times proportional to wind power generation. Means wind flow of wind means wind speed is much more effective for wind power generation. So we have already discussed so many lecture we have seen. So I'm not going to discuss much more about that. I'm going to discuss how this velocity is going to impact this future what is that future hydropower sorry wind power generation that we are going to see. This is the mean wind speed of Indian atlas given by global wind atlas in University of Maryland has given this point. This how wind is varying for Indian subcontinent. So later we will see. This is mean wind speed of India. This in latest we have developed for January, February, and March. This is the mean wind speed atlas for India. How it is varying with the grade scale, very finer grade scale, mean 0.25 into 25. Mean that grid size what we have seen grid boxes. Each and every grid boxes is 2.5 kilometer to 2.5 kilometer. So each and every grid boxes we have mapped to develop Indian mean wind speed condition. Here the in right side we can see the wind power classes. He little bit hazy. Sorry for that. So we can see that how wind power is generating in that present scenario based on the different wind speed. We can see this is the wind speed condition and this is the power generation density we have plotted here. Yeah, this wind zone, Indian wind zone. We can see this. This is Indian wind zone. So we have seen that 50 over 50 is maximum wind speed we can see in coastal coast portion, means in eastern coast, all eastern coast condition, and from some western coast condition, and from Himalayan condition. But in monsoon, and in some monsoon cases, we can see that it is varying. Means hazardous wind, it is coming from north direction, some coming from south direction. So it used to change its direction based on in means monsoon and summer or whatever it is. So we need to develop, we need to adopt this wind panel and its technology based on this changing condition within a decadal or within up to means 2040 where we're going to project. So to project that, what we people used to do means this we can see now it is coming. Yeah. So two blade, three blade, what I have discussed, and four blade condition we can see. When we will use two blade condition, when we will use four blade condition, when we will use three blade condition. Means this total circle, we can see this total circle is 360 degree. This total circle, when in polar condition, we know in climate change, with the climate change, in normal earth surface, wind can flow in hazardous direction, like that we have seen, in these pages. In different direction it can come. But in polar cases, means polar cases, we can see only with time also, means up to upcoming future, means up to 2040. That is not going, melt will be there, but that is not going to affect the wind direction of polar zones. So in polar cases, mean north pole and south pole, towards north pole and south pole. So there we used to keep only two blades. Means why? Because that it flows with the particular direction, so that flow will come through that direction only. But in cases where just after a few thousand kilometers from the polar, so we can see some abrupt condition. So that time we used to install that to means that angle will be covered by each and every angle. We used to cover if three blades, so it each and every two blades, angle between two blades will be 120. So each and every flow, if will comes, so that 120 blade, that will not divert more than 40 to 45 degree. So that diversion will be covered by one blade. So with one blade will move, second blade will move. So based on that means methodology, we people used to develop three blade condition. Right now we can very rare four blade condition we can see, because four blade in ancient time, four blade condition and multiple blade condition was there. What is the profit of four blade condition? Means each, if any direction or any direction flow is coming, or very low intensity flow is coming also, it can rotate and it can generate the flow condition. But what is the drawback of this? It has four blades and many number of fancy blades, so it with some high flow condition, it can broken up. So based on that, presently we are not using four blade condition, but in ancient time we used to use four blade condition to generate, if any flow is there, any flow of wind is there, means less than 10 to 20 15 degree, or near about 7 degree, we can generate the flow, means generate the flow and generate the energy. What are the microcrystalline perspective of wind power generation? Wind power generation means first point is wind direction. Obviously, we'll see in later phase. Wind direction means northward wind flow. Just we have seen northward wind flow or eastward wind flow in Indian map. We have seen. And seasonal variability of wind. Sometimes in summer season it flows from northern direction. Sometimes it flows from south direction. Sometimes it flows lesser in wind speed, but sometimes it flows from eastward direction. So to do that, each previously people used to adopt. They used to put all the windmills in the same direction. But after this realization, after 2014, the what Indonesia did, they kept all windmills in within the 90 degree angle. What means all they have 2000 some in that power project they have kept 2214 sorry 214 windmills. So each and every direction, if they haven't kept in a same row, they kept in hazardous manner. So if any direction will come, some will work and it will give energy, and some will not work, it will work very slowly. At least it will flow, it will generate the energy, means electricity or whatever in a wind energy in all that time, in all the season. So that is the seasonal variability of wind direction. We can get profit of that. In previously we never used to use, we used to put in the same direction, so it used to create in a particular time. That is the drawback of that. So next, seasonal variability of wind speed means in sometimes we used to get wind near about 50 in the same place. Sometimes we used to get 40, sometimes we used to get 10 also. So that is the drawback of this point, means wind energy generation. Next is the involvement of randomness of daily flow direction. Means daily wind flow direction, some hazardous flow will be there. So to remove that hazardness, that what we have discussed in the previous point, they used to keep, we need to keep not in a single direction, we need to keep in near about 90 degree, all should be covered by 90 degrees. So each and every direction of flow will be utilized for wind energy generation. That is the point of this future adaptiveness. Next is the variation of wind speed and the direction in the near future. That we will see how in near future we will see how flow will be varying. So you need to download that data set. We are taking from NASA data set, NASA satellite data set, and so based on that we are projecting up to using some statistical platform. So we are, they have projected and they kept up to 2099. So we are considering up to lifetime up to 2040. So we used to adopt up to 2040. Based on that, how flow is varying, when speed is varying and when direction is varying, we need to adopt that technology also. So these are the some examples data I have kept how to extract that wind miles. So if you'll see, we'll go escape how to extract that condition. So we'll use this point. This is the software to see how this all solar radiation and this purpose for solar power generation, and I'm going to use wind speed for wind power generation, and precipitation, obviously precipitation on all other aspect for hydropower generation. So how it is varying for future prospect. So here you can see, here I have some, this panoply software is for to see how the present, future, and means near period or future period or present period, how it is going to vary, whatever NASA has projected. That one we are going to consider for our project. So this we can see if it is visible. So 2006 to 2055 means last in F to end, we have some projected files. So based on that, this is a radiation and this is temperature max. So this we'll see how much it is varying. So we'll open this. I've selected whatever lat long we can see, and we'll view this point. Here we can see how much this lat long is varying. So each and every table and labels we can estimate for month wise how much month it is deviating, and finally we can do this source file. Okay, rdls plot. Yeah, it is taking time. So we can see this variation. I think it is visible to you. This surface downscale shorter wave radiation, solar radiation, how it is varying for this I kept for this is for 2006 to 2000. This RCT6, what we have taken, we have seen in low flow condition hydropower analysis. There are two times, RCT 4.45 and 85 was there. This is in between, means within the band condition, means 60 and R1 means I1 means one time run and one time simulation. So this is the surface downscaling solar radiation, solar wave radiation. We can see this is the projected surface, or how much it is varying for each and every surface. What is the value? We can see this here. And based on this is written in R coding. So based on this coding, we can extract the particular our for our zonal condition. Means how we have seen in a few slides before, the how it will vary for our Suban Rekha, or how it will vary for our Satluj River basin. We can extract that point. Each and every grid cell also for means 5 kilometer by 5 kilometer, or for a whole surface, means whole water set we are according to our project. So we are calculating for our uh, water set basin, means river basin wise. So based on that we can extract for future purposes also. So these are the sorry for that. These are the way. This is the website where we can extract the data set for future purposes. This is the website of means CMIP5 dataset I am using for our project. Here we can extract. You also can extract. You should have login ID, and you have to extract means project the dataset, means solar radiation what will going to be projected for Indian region of the subcontinent. We need to extract the dataset or precipitation, solar radiation, wind speed, eastern what wind speed or northern what wind speed for wind speed, for wind energy project power plant, or for hydropower generation, that precipitation and all other meteorological component like uh, means, evapotranspiration, all we are going to collect from here. So then we need to extract this data set, means project data set from here. Like each and every model for future scenarios, we need to calculate this one. Then we need to collect each and every model data set. These are some simulated model data set they have kept in their experimental family. This is called experimental family. So and the model we have to choose what you have to going to choose for your your purposes. What will be for that? You need to do proper downscaling. And downscaling means you need to take it towards your basin. Means it is a, we have seen that panoply. It is giving for a whole earth surface. So you need to downscale up to your basin level, means up to grid box. First grid box level means 2.5 kilometer, 2.5 degree means 50 kilometer by 50 kilometer. Then up to your usable level means 0.25 kilometer by 0.25 kilometer. So based on that, we need to select our models, means whichever we are going to use. So here I have used for access and CSIRO project. So we need to select those points, and experimental family and control means for future means up to from from 1850 to 1976. And historical I'm using for, already we have discussed historical for generally they used to add up for historical for 1976 to 2005. So we are also using the same. And RCB scenarios for future means for different RCB component means for 8.5 or 4.5 or 6 RCB scenarios. And time frequency, sorry, time frequency for daily time scale, or you want to extract for monthly time scale, or you can extract for hourly time scale also, 6 hour or 3 hour time scale also we can use. Next point, we can see this daily time scale means CMIP 5 time scale. Next one is ensemble scenarios. So we can see this variable, which variable we are going to use. This is for quality aspects, mean different quality aspect, which one is boron, carbon monoxide, carbon dioxide, whatever it is extracting. So that we can see this point is here. This is useful for us. This is northward is near surface, northward near surface wind speed. Means how in towards which flow is flowing towards north direction, that we are going to consider. And northward near surface wind speed also we are going to consider for this for hydroelectric or wind power generation. We are going to use this first point, means northward near surface wind speed. This second point we are going to use for wind speed, but for hydropower generation, whatever is for useful for hydrological modeling. Next point, when we'll get this kind of data, so we'll get some data set like this. We'll extract the data set. So this we need to add to cart, means we need to purchase, but if you have login ID, you can get this data set. So based on that, you can extract each and every point data set. So and you can extract for up to 240, and you can project that for your solar power plant project, or your wind power plant project, or hydro power plant project for future access analysis. When you are going for, here you can see from easternward winds, easternward wind speed also we can calculate this point. This easternward wind surface and easternward near surface wind speed also we can extract. These are the data set. It will come after the what we have opened through Panoply software, that we can extract from each and every data point. Means this we can see from 1950 to 1959. Means like decadal years they have kept. Mean 1960 to 1969, 1970 to 1979. So you need to club and you need to analyze for historical how much variation was there, and how much will be projected for future period. Means when we are going for means RCP scenarios next year. This is the RCP scenario, this 104 you can see for 2000 to 2005, and for this is for control scenarios 1850 to 59 like that. We can get the data sets, different data sets. Next point is this one, surface. This is the wind speed. This is the wind speed for control scenarios. Means wind direction and wind speed we will get from this kind of file. And the next point is for this R1 I1 P1 means simulation 1 for that particular scenarios, and iteration 1 and project 1 file we can get from here. This is the different models we can see. CMCC, CMS, different institute name will be involved, like Max Planck Institute, MPI, and CSIR or India. So this all will project the future scenarios, and they used to keep to CMIP5 data set that will be projected for future aspect. Similarly, like that, same data set we can get from here also. You need to select that particular file, and you need to download for different version is there, HTTP or OpenDAP data set. Next is for eastward near surface wind speed also we can get. Eastward wind speed also we can get this because eastward wind, this we will select for wind energy calculation. This eastward near surface wind will consider for as a component of input to the hydrological component, means for hydropower generation. That kind of consider this first point, and the second point we will consider for wind power generation component. Next is this will go give some experiment that geothermal energy perspective. So geothermal energy perspective is that geothermal energy is that when in near about polar cases, means where seasonal variability is much more. So there they used to put one insulation, and they in from house or power plant they used to keep one in towards the earth core, and that they used to consume the temperature from the earth core, and they used to take use for their home remedial use or industrial use, and they used to return back this lower temperature to the earth core. So that is the geothermal power process plant. What we can see, this is the diagram of geothermal power project plant. From earth core they are taking some stream recovery, means water injection is there. So they are taking the earth energy, means as a term of heat or temperature they are consuming. Later whatever is lower temperature they are sending back to the earth surface. Means already earth surface is having much more temperature, so we are taking that comes under geothermal power plant, that is comes under renewable energy resources. So these are the geothermal power plant for Sarula power plant. So that is from it is from Indonesia. This is developed long back. They have developed this geothermal power plant for total city. This is the for total city. They have developed this. What is the formula to calculate this geothermal power plant? The 3-4 method is there. Basically, people used to consider for USGS method. USGS has they have United States Geological Survey Organization is there. So they have gave two different methods. First is thermal energy stored in the reservoir method, and second is reference temperature method. So first point is that thermal energy storage method. According to storage condition, it used to work. So that is that. Hmm, Sorry, I have kept opposite equation. So this lower is the thermal energy stored equation, and this first equation is for reference temperature. Thermal energy store condition we use this given this formula based on the journal paper of Muffler proposed by 1978. This is also reference temperature condition also proposed by Muffler in 1978. He has discussed about these 2 points. This QRV RSV stored thermal energy geothermal power condition, which is based on CV into V into multiplied by RSD minus T ambient. That is totally in kilojoule. Means that CV is the coefficient of that thermal conductor, whatever we are keeping in that down to earth surface, that is varies from uh, point 667 to point it can come up to 0.89 also. So that point is varies from that is kind of efficiency of that conductor. Next is the voltage. It's a difference in temperature. We know that voltage is nothing but difference in phases. Means that our room temperature, wherever we are using, and that earth core temperature in that particular depth, how much temperature is there. So we need to subtract that is considering as a voltage to that TRSV, and TRSV minus T ambient means ambient means ambient temperature. TRSB represent for that reservoir where we are storing that reservoir temperature, wherever we are getting for that storage. Here we can see this is the reservoir storage, the storage point, and this is the conductor where it is taking that towards the earth core surface. So T reservoir minus T ambient temperature we are subtracting, so that is comes under thermal energy storage in reservoir method. Next is reference temperature. Reference temperature method is that in this geothermal volumetric resources we are assessment, because we every time no we means we can't get this point ambient temperature. So what we are considering, we are taking 15 degree. He has calculated, means Muffler 1978. He has taken our T reference temperature as a 15 degree centigrade. So that he has considered for reference temperature, and he has calculated this for same, all are same, and CV is the coefficient, and V is the voltage, and TRSV minus TRF. So that they have calculated, he has calculated using this formula, which is used by Muffler et al. And also that technique is adopted by USGS, which is using throughout the world, and as well as this Indonesia, this cellular power plant. This is the earth core. You can see this how it is working. This is the earth core surface. So how this temperature is to vary based on different kilometers. So temperature gradient, we can see how much 1 degree it is to vary from the ground surface to earth core towards inner core. Here to means our surface means free surface where we are tilling, then used to go to mantle and inner core, outer core, then it core to outer core. So this temperature, it is based on depth. We used to keep this inside. So you need to consider this depth versus we have kept the temperature, how it is varying. So how much depth we will provide, we will get up to that much portion where our earth means that conductor can survive in that condition, means that up to that conduct up to that much temperature. That is the drawback of this. So this material should be uh, should survive in that process. V5, this is the model. This is the platform where we can get the CMI V5 dataset. This is a coupled model interface dataset, 5 future dataset. So uh, this we need to log in and you need to go for couple model dataset. Just you need to come to Google. So just open it and this will come for your project, whatever you want to need. This project you need to see the open, then you need to choose for this is CM IP5 or different lucid data set also. This is for different positions. Means, they are varying from different product you want to use, means our normal output one means run one, output two means run two, and unsolidicated, that is mixed combined. So then we don't know about this point because which one whoever kept in which domain, so we'll leave this point, means it will clear data set in our ASEAN data condition. So you can choose for CSIRO or later you can go for this one, Max Planck Institute. This very other data select. Next, model, different model. What is the different run model? So you can select according to that. Let us consider for access model and our CSIRO model for Indian condition. They leave that point because it is not we want for all conditions. Next, for experimental family, means for control, means for from 1850 or 1800 to before history period, means 1970 or 76. So we'll select that one, and we want that one also. And we want historical also, means 76 to 2005 around. And we want frequency. If you want a very accurate calculation, you go for 3 days, but 3 hours, sorry, 3 hour and 6 hour condition. But in other data set, you will not get for 3 hours. So better to choose for aerosol. So we want also leave this CMIP table stable in that we want a daily time step. So we have select daily ensemble means that is simulation run and it has it runs what is that project number, it is that is zero, that kind of variable we can see. So we want for all, so we are selecting all. Next, the variable we are going to select whatever variable is there. So here we need to we want all the for all the surface, so we leave him temperature is there, but we want near surface wind speed or solar radiation. So we'll go for that. Uh, yeah, northward ocean wind heat, not that one, not that one. Wind speed we need to get. Mm, So somewhere we'll get in shorter direction in surface near surface wind speed we'll get. So after that we'll extract each and every value. Next we need to search for that. That for all means precipitation also will come and wind speed will come and surface near surface temperature also come. Solar radiation will come. So we need to choose from this all the list. Means whatever is if we see if we open each and every file, it will come like this file in panoply. So we can if you see panoply using that this software to 50 kilometers 15 to 50 grade scale or 5 into 5 grade scale. According to that, you need to select. Any questions or anyone interested to ask anything?
Thank you, sir, for your very informative sources, wind, hydro, solar, and geothermal. I would like to request all the participants if they have any questions regarding this session. Yes, sir, you are clearly
Yes,
audible.
sir.
Sir, my question is, sir, which one is better, sir? Whether it is spin blade or the three blade?
We are using people are using according to US GS geological survey. They are using for sir, for polar condition. They are using two blade condition. For
Okay.
polar where the wind will not be hazardous. Means wind up to 2040 wind will come in the same direction. But in our country like India, we have hazardous wind direction. Means direction will vary, wind velocity, wind speed will vary. So that hazardous condition will be there. So for this cause we can see that PPT we have seen one we have drawn one circle that is varying from total angle is any direction. Means that will not maximum variation in wind direction will be 40 to 45 degrees. So we are trying to capture this wind within this 120 degree. So based on that, we are develop in maximum cases we are putting three blades. And the next point is that one mechanical point of view is there. In high wind speed, two blade in but in means this whatever in normal plane they are using for three blade condition, sir. So in three blade condition, if high flow and hazardous wind speed is coming, so some sudden storm event is coming, so that can't bear that. Based on that, so we are using three blade condition. So for my point of view or whatever for our Indian projects they are going to.
Thank you, sir. Hope our eminent speaker has clarified your query. Once again, thank you, sir. Any other questions from the participants?
No, sir, no questions.
Thank you.
The last session is available in the chat box, and there is one overall feedback link for the total 3-day FDP. You have to fill the both form, and after 2 minutes we will start the validatory session. After the o'clock tonight, you have to attend the test, and 80% marks is mandatory for getting the certificate. Right now, after 2 minutes, we will start the validatory session. Thank you. of Global Institute of Science.
Okay, am I audible?
Yes, sir.
Very good afternoon, everybody. I am Devajyoti Mukherjee, in charge of Mechanical Engineering Department from Global Institute of Science and Technology. Heartiest congratulates, get a comprehensive knowledge about this FDP. We had jointly conducted this FDP from Mechanical and Civil Edge is frequently conducting this type of FDP with the vision of ensuring skill development by imparting quality technical education so as to create dynamic human resources. And our institute's mission is imparting creative learning by innovative teaching methodologies to expose the talents by the way of WBSCT, means West Bengal State Council of Technical Education curriculum. Now, I want to say my departmental vision and mission. First of all, I want to say vision, that is to achieve excellence in mechanical engineering by number one, to offer quality education with supportive facilities to produce technically proficient engineers to serve industry. Number two, to motivate students among students with societal and environmental concern. So that is our mission and vision of Mechanical Engineering Department as well as Institute. After that, I want to say in part number two, the students will execute their assignment effectively as individuals and team members in multidisciplinary setup leading to a common goal. Just this, no more today. Again, I heartily congratulate to all conveners, co-conveners and faculties involvement in this FDP. Okay, thank you very much to all of you.
Thank you, sir, for your valuable speech. Now I would like to request our respected in charge of Civil Engineering Department, Mr. Chinmay Ranjan Das, sir, to say a few words about our FDP and his department.
First of all, I'd like to thank all the organizing committee for giving me this opportunity to say something on this 3 days FDP program on radio. I would like to immensely thank all the eminent speakers to share their knowledge among us. I hope all the participants have been greatly influenced by the lectures delivered by them about our departmental mission, vision, and characteristics with the potential to accomplish professional and experimentation tasks in civil engineering and associated fields with concern on collaborative and creative viewpoint and to engage themselves at all levels to the civil engineering field to transmit soft skills, leading characteristics and professional morals between the graduates to control the project autonomously. And third one is to promote graduates to take part globally. And last mission is to negotiate with the current problems and to fulfill the societal requirements. And our department has 4 program educational objectives, and those are to give standard learning and awareness in the current science and technology to tackle the problems in civil engineering field and to help the community. Second one is to transfer the information, inventiveness, professionalism, confidence, and last one is to inspire the students to take part in further education and creative experimentation related to the projects. That's Mondal, Assistant Professor of Global Institute of Technology, Global Institute of Science and Technology, and Mr. Alok Chakraborty, Assistant Professor of Global Institute of Science and Technology. Somukanti Mondal belongs to Mechanical Engineering Department, and Mr. Alok Chakraborty belongs to Civil Engineering Department. And the co-conveners are Mr. Shubhankar De and Mr. Saurabh Dal for giving me this opportunity.
Thank you once again, sir, for your valuable speech. Actually, our main aim to conduct this FDP, we have conducted this FDP with some eminent persons in their respective fields. Now, I would like to request our respected Registrar Sir, Dr. Subimal Das, about our FDP.
Good afternoon. First of all gratitude to our Honorable Chairman Sir, Dr. Lokal Sir, Dr. Bikramjit Choudhury for their kind permission. Dear teachers, colleagues, and everyone who registered this acknowledged the contribution of those who worked really hard to make this event possible. I, Dr. Subimal Das, Registered of Global Institute of Science and Technology, on behalf of this institute, extend my science and technology was set up in 2006 by Indian Center for Advancement of Research and Education. It was set by our Honorable Chairman of ICARE, Dr. Lakhon Chandra Seth, ex-MP. It is affiliated to West Bengal State Council of Technical and Vocational Education and Skill Development and approved by AICTE. It is one of the premier technical institute of West Bengal, which has been recognized for imparting finest technical education to its students. GIST has developed a good brand of leadership in providing value and need-based education to the present and future generation of our society. From 2006 to 2021, near about 6,000 students passed this organization. They settled them in different corners of India. Some of also they engaged themselves higher education. Some of them engaged entrepreneurship. On behalf of my institute, I extend a hearty vote of thanks to our guest lecturers who spread times from their busy schedule to grace the occasion. For 3 days, we had an opportunity to hear your thoughts, and this will surely encourage us in all our future endeavors. I also want to thank our today's guest speaker, Dr. Abhijit Bardhan, Assistant Professor, Civil Department in Bharat Institute of this day, enlightening for us. Your deep and intellectual way for imparting knowledge has added to the glory of this event. I want to appreciate their efforts for making the event informative for all of us. We have got a lot of information, deep insight into the topic, and revealed some interesting facts. I must mention our deep sense of AMPYR Energy Tech and Dr. Santop Giri, Associate Professor, School of Applied Science in Haldia Institute of Technology, to their speech idea. We are all inspired by your great work. An event like this cannot happen over backed by a team of very proactive and dedicated staff. A special mention to our respected principal, Dr. Bikramjit Choudhury's untiring efforts. I am, but not the least, a big thanks you to each one of you who made this. We thank you for being with us, advisory board and organizing committee of this FDP program, and also thankful to Mr. Soumyakanti Mondol, Assistant Professor, Mr. Saurabh Das, Assistant Professor Mechanical, and Mr. Shubhankar De, Assistant Professor Civil. All the speakers have beautifully ahead. Thanking you.
Thank you, sir, for your kind the future. Now, I would like to share some information with the participants. There is the last session feedback link available in the chat box, Google Meet chat box. After that, after some times, a test link will be given in the WhatsApp group. You should appear for the test. There will be 10 questions. And with due respect, thank you once again, all the speakers and participants who are present in this FDP of Science and Technology.
Thank you all participants for staying with us. Just a minute. Is my voice clear? Is my voice clear, sir?
Yes, sir.
Okay. Thank you all participants for staying with feedback form, as we can improve our future events more interactive. It's near the end of the year. We wish you all participants and our beloved eminent speakers a prosperous happy new year. So please, sir. Okay. So please try to open your camera, sir. Okay. From the side. Okay, sir. Thank you again. And it's impossible to say goodbye, but now it's time to say goodbye. See you soon. Thank you.
Thank you.
Richard.